Hello friends, good morning. This is Professor Chaubey, Professor Chaubey's physics class. Today we continue our earlier discussion. We will talk today about semiconductor devices. Semiconductor devices. First I will talk about the forward biasing of PN junction diode, then reverse biasing, characteristic of junction diode, then further we will go to the rectifier, etc. So we first talk forward biasing of PN junction. As we know that we represent PN junction diodes say just simply and we bias such that this PN junction diode, that this battery of this terminal is positive here and this is negative. And we connect a variable resistance just to control the current. Okay, we apply from this battery the voltage, DC voltage, and we increase the DC voltage. So we see this, when the P end is the positive, means holes are getting forward push, a force towards moving towards N-type material. So PN junction diode, holes moving means electrons coming to other direction. Electrons are filling the vacancy and electrons are moving. Holes are diffusing in other direction than the electron. Actually, hole is the theoretical concept, no physical entity. It is just vacancy of the electron. Electron fills that vacancy and moves to the opposite side of the hole. So that current flows. And you can see that if we draw a curve between the voltage and the current, axis is the voltage here, and we can see that from here, that's zero, the current increases like this. Current is in forward biasing a few milliampere. Voltage increasing, current increasing, but don't increase voltage beyond a certain limit so that current becomes very large. If current becomes large, it may burn the material, silicon or germanium, whatever semiconductor you are using. So that may burn and then finish. Your device is finished. So increase voltage up to a certain limit. Current may be few milliamperes, maybe 10, 20 milliamperes or 25 milliamperes like that, not more than that. So this is the forward biasing, means the flow of current is just majority current carriers are electrons and minority current carriers are holes. So minority is very, very small and minority will move when it is reverse biased. When forward biased, the current flow is to the majority current carriers. Majority current carriers are electrons. Electron. So current, as electrons are large number free in N-type material, that is also called donor. It donates to the system. It donates electron to the system. And other material which is P-type material, it accepts the electron. So it is called acceptor. Means it has got a vacancy, that is the hole, where we have doped a P-type third group material into fourth group material, there is a vacancy of the electron. So that is filled by the electron, and then electron moves opposite to hole. So that is the minority current. Minority current carriers are holes, and majority means just you have fifth group element, say arsenic. Arsenic has got 5 electrons. Silicon has 4 electrons. So 4 electrons have covalent bonding and 5th electron is free. That 5th electron is just free to move, to flow just like a current. So large number of arsenic 5th group making 1 electron free, that electron is available for the conduction. So that is the current flow in the forward biasing is due to the electron flow, and that is the majority current carriers electrons. So current is also large, means a few milliamperes, and that is the forward biasing. Current voltage increases, say 10, 15, 20 volt, current is say around 10, 20, 15, 25 milliampere. Well, just opposite to this is the reverse biasing. What is the reverse biasing? Reverse biasing means now you have connected battery just opposite to the battery connection you have changed, means this was battery earlier positive, now it is negative to this side and positive to this side, and we connect similar variable resistance to, or we can connect a milliampere, a current meter also, milliampere or microampere. So this is negative. So now the potential is opposite. So means previously the current was due to the flow of electron, now the current will be to the flow of the holes which are in minority. So now current due to the holes flowing or electrons filling the vacancy of electrons, which are holes. Holes are just theoretical concept, not physical entity. It is deficiency of electron. So holes are filled by the electrons, and these are in minority. So minority means current is now in the minority, means due to the hole. So current is order of, now we have negative potential. This is negative side, this one positive side. So now we increase the potential from 0 to 2, 4, 6 negative side. And current is almost constant because it is small current due to the minority current carrier. And then suddenly current starts increasing and current becomes very large. That is the reverse biasing. This current is voltage negative B. This current is a microampere. This was milliampere, this is the microampere current, and it is almost constant, 4, 5, 6 microampere, and then at certain voltage, current increases tremendously, current becomes very high, and that this portion where current is the very high, this region is the breakdown region. Means breakdown of junction diode happens, but this is also called JEE reaction. Here a diode working here is called JEE diode. Breakdown means suddenly breakdown takes place, means large number of electrons becomes free. Covalent bonds are broken because the potential becomes very large. So large number of bonds are broken means large number of electrons are free. So suddenly current becomes very large. This current is due to the flow of electrons. And here, now in the reverse biasing, what happens? At a certain voltage where breakdown happens, potential across the resistance becomes constant. And this is JEE reaction, means this is used to produce a constant voltage. We have JEEers of 6 volt, 12 volt, etc. And for 12 volt JEE, a breakdown takes place at 12 volt. For 6 volt zener, a breakdown takes place at 6 volt. So that is used to give a constant voltage supply. Zener diode. Zener diode, a diode in the reverse biasing at zener breakdown voltage works as for a constant voltage source, and the current is large, very high due to the majority current carriers. It is breakdown means covalent bonds are broken and large number of electrons are free. But in the beginning from 0 to minus 5, 6 volt here, current was almost constant, microamperes, and this suddenly increases very high. So this is reverse biasing. So we can have a diode, we can use as the reverse bias. Remember that reverse biasing current is very small. We don't use the diode at the zener voltage. We use only when we want zener function. Otherwise we use reverse biasing diode at the lower voltage when the current is constant, microamperes. Remember that this current was due to the flow of minority current carriers, and remember that minority current carriers means holds current very small, and that is called resistance is very high. So current is very small, means diode has got very high resistance. And when forward biasing, current was milliampere, large current, that means the diode resistance was small. So in the forward biasing, diode acts as a small resistance source, while reverse biasing, diode acts as the high resistance. And this is the method also of checking the diode working or not. I have been asking many times to the students, also to teachers also in the lab, whether you have large number of diodes in a small box, your system is not working. While doing experiment, how you will say that my diode is not working and I want to replace this junction diode? You will go to the lab assistant and ask, give me new diode. But why? How to check? But almost 100% students or teachers also face answering this thing. I many times said that you have only one multimeter and a diode. I want to know whether this diode is okay, working or not, or should I replace? The answer is very simple. You measure the resistance of the junction diode using multimeter. Just by changing the terminal, you put the positive on one side, negative on one side. You see the current is high, means low resistance, diode is working. Reverse the terminal voltage, current becomes very small, means reverse biasing, diode is working. But if both sides current is same high, it means it is burned. Or no current, both sides zero current, it means it is burned. One side positive forward biasing current must be milliamperes, other side current should be microampere. If this is correct, then diode is okay. So just testing diode using multimeter is very simple. And you can use the multimeter and test your diode and replace if it is not working. So simple. Means diode has almost infinite resistance, reverse biasing, and very low resistance when it is forward biasing. Now we have say, we use diode say also as a rectifier. I say here half-wave rectifier. And I will explain what the half-wave rectifier and what the full-wave rectifier. You see that rectification is a process, you see. Rectification is a process, that is the conversion of AC into DC. That was alternating current, you want to convert DC current. Alternating current, you know, have a frequency of 50 cycles per second, that is plus and minus, and DC has direct current, means constant current, linear current. I connect now say a PN junction diode Just very simple. Here, a battery or a transformer. This is a transformer. Low voltage transformer. So this is giving alternating voltage, alternating current, plus minus. So here, when this is positive, plus side, this side, plus side, what happens? This conduction will be there, diode conducts, and there is a current flowing in this I, and here I current flowing, R resistance here, there is IR drop here, and we get a potential drop here at 2 point V IR drop. So IR drop here, we measure the potential here, means if we connect AC at the PN junction diode, its positive cycle is forward biasing the diode, and we get the current here. Current, and we get a voltage drop here. This is the, when this is the input is like this is input, we get output, a positive, a variable current. Now, half-wave rectifier, it comes negative cycle this. When this becomes negative and this becomes positive, it is now reverse bias. Reverse bias means diode acts with a very high resistance. Current becomes microampere, almost negligible potential drop here. So this negative side here, we don't get, sorry, this is output. This is output. This is input. So for this portion we get output. For this portion, reverse biasing, we don't get anything here. And then when again positive comes, the polarity changes. The diode becomes forward biased, and then again current flows through resistance. IR drop is there. So positive half cycle, again we get output there. Like this, again negative comes, no current, no voltage drop, and we again get for the positive portion. So we have input alternating like this. We get output a variable current, not for this negative portion, only for the positive portion. So for AC, it is variable positive one direction current. One direction current. One direction only. But this is variable, because here nothing. So fluctuating, you can say fluctuating DC. For AC, here we have fluctuating DC. So this fluctuating DC is not useful. What to do for the half-wave rectifier? Well, what we do here, this voltage which is here fluctuating, what we do here, we connect here, say, this voltage, we connect to a capacitance and to a inductance L and C, and here also capacitance. And further, if we measure the voltage here, we can connect a zener also here. Say, this is a zener. And this is the output. How much output is required? We select a zener of that voltage. If we want 6 voltage constant battery, we put a 6 voltage zener at the output. Or 12 volt battery, we put a 12 volt zener there. But this fluctuating voltage here is fed to the two capacitance inductance combination. You know, this capacitance inductance combination is called filter circuit. What the filter? Filter is filtering the alternating current, and it is passing a constant voltage DC. AC filter means we want what we want. We want constant voltage. So this was the fluctuating. It looks like that this input becomes and the output just like this constant voltage. This is a DC. How it becomes? When this is but this is fluctuating. So half-wave rectifier is not very useful. Not very useful because for half cycle it is not giving anything. But you can use this to make it constant. Means when the voltage is decreasing, the charge capacitance and the magnetic inductance gives the induced potential. So that when the potential is decreasing, it gives induced potential and we get at the output potential. When the potential is increasing means from lower to higher, again changing current means inductance gives the induced potential, and when potential increasing, it decreases. When potential decreasing, it increases. So that way inductance and capacitance charged to constant voltage, they give here somewhat a constant voltage and fluctuating voltage becomes almost constant type. And when we connect the zener diode, well, zener gives the constant voltage, whatever zener is 6 volts or 12 volts, same. But you remember, half-wave rectifier is not a very useful device because for half cycle it works only. So we should have either we should use either two rectifiers or we use also bridge rectifiers, four diodes making a bridge. That is also a power supply rectifier. So what is the full wave rectifier? Well, full wave rectifier. We can see that the full wave rectifier means when we connect AC to the diodes, we get current or voltage drop at the resistance for total current, total AC means positive and negative also. If we get this output for the full voltage, it is called full wave rectifier because half positive part also giving current and half negative part also giving current. So how it happens? That we have to understand how this happens, how this full wave rectifier works. So means that we have to connect say two diodes. So full wave rectifier is that I connect here a PN junction diode like this, and here also I connect one diode. And in the middle of this we connect just like a inductance and inductance or just some load, you can say. Just we have a load, just earlier we have resistance here, so we have a load. It can be inductance or resistance combination or like this. And here we have, say, transformer, just output of the transformer or secondary of the transformer. These are the two terminals, one terminal, other terminal, and this is the center taping of the transformer. Center taping. Here we have a soft iron core in the transformer, and this is the primary of the transformer. A step down, then it has a small turn. A step down turn. So this is the 220 volt AC. This is a step down. So it can be any voltage, maybe a 50 volt, 20 volts, like that. A step down transformer. If you want low voltage, if you want high voltage, this diode will not work. A step down transformer, mostly for the low voltage power supply. This is the, you see now, input here, as see here, the central stepping here. You see, this is zero, this is earth ground. This is the earth or ground point. And this is this end is positive, then this end is negative. So when positive cycle of AC comes, this diode D1 will have conduction through this resistance and voltage drop will be here. And this is negative. When this is now negative, this is positive, this diode conducts because it becomes positive, this doesn't conduct. So for half positive, half cycle, this diode will conduct. For the half negative cycle, this diode will conduct. So for the full AC, that is the positive and negative. For this is the diode D1 conducts, for this is the diode D2. This is the diode D2 and this is the diode D1. So positive half cycle, this D1 conducts and gives a voltage here. And for the negative half cycle, this D2 conducts and gives voltage here. So across these 2 points, we get a voltage plus, and this is the ground, 0. So we get a constant voltage here. At R, we get voltage drop, that is IR, for both the cycles. Positive and negative. Means if this is the input, then you can see that this is the half cycle positive, negative also current flowing through diode D2, which is giving same voltage here, like this. So this is the output. And then this is connected. So output is, for input alternating, we have DC, direct current output, but fluctuating. Remember, this fluctuating voltage is not very useful. When this is coming down from here, where we should get like this voltage here. When this is increasing, we should get decrease like this. So here, almost average. In place of this fluctuating, we get output like this. If we connect filter circuit like say capacitor, it means at the output here, this output voltage here, so we can correct. This is not connected here. This is not connected here. Here we can connect, say, like a capacitor. This resistance is connected to a capacitor, C, and inductance, and again capacitor, C. So this becomes now voltage, that is IR. But this IR is now, because this is the filter circuit. This filter circuit gives a constant voltage, and the filter circuit output you can use here, this this can be connected to a zener. So zener is connected here, then it gives, this is the symbol for zener, just like, the symbol for zener is just like, here we have just like AC. This end is just like AC. So this gives this zener action. So this constant, this C means filter, is connected this constant voltage to this zener. So zener gives constant voltage because at the constant voltage, breakdown voltage, the voltage remains almost constant. 6 volt zener or 12 volt zener, 9 volt zener. So your full wave rectifier, and then this can be connected just like a bridge rectifier, means you have a 4 junction diode and you connect them such that you get full wave rectifier, but just the connection of them, 4 diode connection is just. So here we supply, we give the transformer, and just here this, and here we connect a load resistance and we get a DC voltage here. So 4 diode connected like this is a bridge rectifier, and 4 diodes are used, so they give more constant voltage, and this constant voltage is connected to the rectifier and to zener diode. So this is the application, one important application of PN junction diode. Full wave rectifier, a PN junction diode, is very useful for producing a constant voltage supply using the bridge rectifier, using the 4 diodes connected together. As I have shown, it acts like a bridge. Current flows in 4 diodes, so this is called a bridge rectifier. So friends, this completes the PN junction diode and its characteristic and its important application as the production of constant voltage, power supply, the rectification. So we will stop here, and in the next lecture we will talk about the transistor and transistor action. What is the transistor action? So thank you very much.